So we have been looking at how we can start to observe our different states or different matter and how we can start to describe our observations. Today we're going to be really drilling down into those little building blocks of matter, which we know to be atoms. Atoms, the smallest indivisible particle that still retains the unique properties of a substance. We often will call them elements, and we can start to connect elements together to make compounds, make all sorts of fun and useful things that we use in our everyday life. So just real quickly, a little bit of a refresher on our building blocks of atoms, and then we're going to be looking at how we can start to describe our different types of atoms. Just as a reminder, protons, the smallest positive subatomic particle. A proton is a 1+ charge found in the nucleus. It has a mass of 1 AMU. So if you're thinking about your particles, the proton's got it all. It has a mass and it has a charge. We find it right there in the crunchy nucleus per our Ernest Rutherford gold foil experiment. Also in the nucleus is our neutron. It is our neutral particle found in the nucleus and has a mass of 1 AMU as well. And reminder, AMU just stands for atomic mass unit. This is our tool for kind of describing the size of these particles. It is defined as 1/12 the mass of a carbon-12. So we kind of said, here's our carbon-12, 6 protons, 6 neutrons. We'll divide them by 12 and say that each one has a mass of 1 AMU, thus kind of giving us this unit we can use to describe our masses of our atoms. Last subatomic particle to talk about is our electron. It is our negative particle that's whipping around in those outer energy levels. It's about 2,000 times smaller than our proton or our neutron, and we know it to be kind of our main contender when we start to look at chemical reactions as to why we see the changes that we see, because they're on the outside, they're in these energy levels, and they are therefore interacting with the things around them. Cool, so 3 subatomic particles, but how can we then use that to describe our different atoms? Well, if we say we've got an element, it's got 2 protons. That's how we determine whether one element is the same as another. 2 protons would be, helium. We call that the atomic number. It often gets the symbol Z for, I think it's Zygote. It's a German word. Anyway, but it is our atomic number. It describes the number of protons in our atom. Mass number, it gets the symbol A. The mass is all of our mass particles added together. So our protons plus our neutrons will give us the mass number. And charge is equal to the number of protons minus the number of electrons. Protons being positive. So for example, if we had 20 positives, 20 protons, and we had 20 electrons, 20 negatives, well, 20 minus 20 is 0. We have a neutral element or an atom. We have 2 other kind of vocab terms we should talk about just as a refresher. Ions, if you remember, are charged atoms. We've either gained or lost electrons. We're not going to change the protons because that changes the element. That only happens in our nuclear reactions. We're not going to be doing that here in chemistry. We're just going to be gaining or losing electrons. And then an isotope are the same element, but with different masses. And we achieve that by changing the number of neutrons. This doesn't affect any chemical properties because it's our neutral particle. Doesn't really change how the atom acts chemically, but it does change the mass, which has kind of interesting ramifications when we think about tagging radioactive species. So we've got neutrons. Changing the neutrons gives us our isotopes, or different types of the same element. Kind of the prime example of this is our hydrogen atom. There are 3 known isotopes of hydrogen: protium, deuterium, and tritium. Protium, 1 proton. Deuterium is 1 proton, 1 neutron. Still hydrogen, but now has a mass of 2. Tritium has a mass of 3. It's 1 proton and 2 neutrons. Again, still hydrogen, but it has a different mass. So given these pieces, we can start to kind of describe and look at our new piece. I want to make sure sharing is paused. Bring your shared window to the front. Here, let's do this. Oops, sorry. We want to share this one now. Cool. So if we were thinking about kind of our atoms and how we start to describe it, if we had 1 proton, try to put it, it won't go. Hey, there it goes. Our protons, we find them in the nucleus. And so with 1 proton, we would say we've got an atom of hydrogen. We give it Z atomic number of 1. If you look at the top of the little hydrogen box, it's number 1. You'll notice that this is saying it's an ion. Well, why is that? Well, we just have one positive particle right now. It's an ion, a charged particle. We got 1 proton, no electrons. 1 minus 0 is 1. We've got a 1 plus. Let's make it neutral. Let's add an electron. We've got 1 positive, 1 negative. We have a neutral atom of hydrogen. If we add a neutron, it's still hydrogen, still 1 proton, but we now have a mass of 2. We've increased our mass number. So this would be deuterium if we're thinking about our kind of analogy. If we add another proton, well, now we've got helium. We now have 2 protons. It is a different element. We're back to an ion again. Let's make it neutral. We'll need another electron to make it neutral. Now we've got a neutral atom of helium, 2 protons, 2 electrons. Helium we know to have an average mass of about 4, which means we also need 2 neutrons. Again, adding another neutron does not change the element. It only changes our mass value. If we were to add an extra electron on here, well, all of a sudden we've got a negative ion. We have more negative electrons than we have protons. As a result, we got 2 minus 3. This is now a negative ion, which, if you know helium to be very, very stable, it's a noble gas, is not going to do that. This would be a better arrangement for our helium. So just giving you another visual as we start to think about these different particles and where we would find them in the actual atom and what they describe for us. Oftentimes we use, sorry, I want to make sure, okay. We often will use kind of a shorthand method as we start to describe our atoms and our particles. And so we can then start to look at kind of our table, if you will, of our pen numbers. So here's a couple of examples of how you might see this actually represented to you in terms of our pen numbers. Let's do the first one together, and then we can come back and have you try one, and we can compare and see how we're doing. All right, so if we look at our first example here, we've got what we call the nuclear symbol. We're technically missing something. We should actually have our final value here at the bottom. There should be a little 9 here. I apologize. I couldn't quite figure out the formula for that. If we're looking at a nuclear symbol, this top number is always going to be the mass. The bottom number is the atomic number, which we know to be the number of protons. And the top right number is the charge. Excuse my writing here. If we're then thinking about our different kind of values or our different pieces, this one nuclear symbol, it's super handy because it tells us everything we could know or need to know about this particular, in this case, ion of fluorine. We know it's an ion because it's got a charge. So we can start filling in the pieces that we know. We know that this has got a mass number of 19. It's that top value in our box. The atomic number is 9. If we didn't know that, we could look on the periodic table to find number 9, and it would tell us that it was that fluoride. And what's nice is this is set up for us. We know the mass is protons plus neutrons. That means if we want just the neutrons, we can subtract. 19 minus that 9 over here gives us the number of neutrons, 10 neutrons for this particular ion of fluorine. We know that the atomic number equals the number of protons, so this must also be a 9. We know, we know that we've got a charge, protons minus electrons. Okay, all right, we got a charge in -1. Well, I guess we got to do some math, huh? -1 is going to equal 9 minus some number, in this case, x. Okay, well, solve for x. 9 comes over, we'd have to subtract both sides by 9, so now we have -10 equals a -x. Okay, we multiply everything by -1. X equals 10. Oh, okay. Now, you could do all that, or we could think about it in terms of the particles, right? We know that we have 1 extra negative, then we do positives. We had 9 protons, we must need 10 electrons to give us 1 negative left over. Excuse me, I'm in the wrong box. This should be over here. The charge is just that -1. I apologize, I was doing my work off here to the side. Cool. If we're looking for completion's sake here, this element would be fluorine. This is an element or ion of fluorine. Cool. Pause the video for just a second. Try that bottom row for yourself. When you're ready, come on back and restart the video. Cool. As we're looking, this is a little different because we've got the information. We got to work it all the way back to what the element actually happens to be. Well, okay. We know that mass is protons plus neutrons. We've got 40 equals X. We don't know the number of protons, but we can find it because we do know the number of neutrons, plus 20. So X plus 20 equals 40. Okay. Or subtract, right? 40 minus 20 will give us 20 protons for this particular piece. Now we've got some options here as to what we want to, what we might do. Why don't we go ahead and work right to left from our boxes? We've got a charge, great. We know we got 20 positives, try to figure out how many negatives. Okay, well, we could math it, but let's try to reason this out. We've got 20 positives, we want 2 positives left over, which means we have 2 fewer of those negative particles. And again, you can always confirm 20 minus 18 equals a positive 2. Cool. Protons equals the atomic number. I think we have everything we need. If we go to the periodic table and we find number 20, that is calcium. Calcium. All right. So now if we want to do our nuclear symbol, we know it is Ca. There's our calcium. Top left is the mass. In this case, it is 40. Bottom left is the protons. That was 20. And we do include the charge to show that this is a positive calcium ion, so Ca2+. Cool. Nice to work through some of these examples, how you might see this, not in a kind of structural or model form, but actually with values and interacting with the periodic table. Cool. Hope this is helping as you start to think about our different pen numbers as we continue to move forward.